Hello and welcome to another edition of Mr. Viola's Physics Classroom. Today we're going to talk about forces and specifically a review for your test this week. So within forces we had several topics. We had Newton's laws, force diagrams, gravity, and friction. Those were our main topics and we'll go through them all today one by one. So if we start with the first one, we had Newton's laws. So far we've talked about two of Newton's three laws. The first law simply states that an object in motion or at rest will stay in motion or at rest unless acted on by an outside force. So basically what that means is that no matter what's happening, and on Earth this is a little bit different, but an object that's moving is going to keep moving unless an outside force acts on that to slow it down. For instance, if something is sliding across a table, that object would keep moving if there was no friction. On Earth there's always friction, so we really don't have this. This is kind of a perfect case scenario. And then at rest, something that's sitting there won't start moving unless it's pushed or acted upon in a way that causes it to move. The second law is simply the equation F equals ma. So Newton's second law, we did a lab on this where we related force and acceleration and found that the slope was the mass. You could also look at this as a bit more general form of force of gravity equals mass times the acceleration of gravity. This is a little more specific version. This is in situations for gravity. But basically these are Newton's first two laws. His third law, every action has an equal and opposite reaction. We haven't covered yet, so don't worry about that one for this particular quiz. So let's look at these two. What can I do with them? And what is possible? What kind of questions might I look for? Well, besides the obvious, what are Newton's first two laws, you could also look at problems that are designed to test your ability to manipulate Newton's second law. For instance, if I was given a force, if I said that I pushed something with a force of 100 newtons, and if I said that caused that object to accelerate at 10 meters per second squared, maybe I'm looking for the mass. So I would simply take my Newton's second law equation and I would rearrange that to solve for the mass. So I would take 100 newtons and I would divide by 10 meters per second squared and I would get 10 kilograms. And that would be my final answer. So this is a pretty simple one-step algebra problem where I'm just rearranging to solve for different variables. If I was looking for an example of Newton's first law, it would mostly be a description of an object either in motion or at rest, and why or why not it would stay that way, or why it would or would not stay that way. Moving into force diagrams, we've already had a quiz on this once, and it's basically the same thing. You'll get some questions. So for instance, as a refresher, if I have a book sitting on a table, I have the force of gravity, and I have a normal force. If you're not a great drawer of lines, and you want them to be equal, put a sign through them so I know that. If you don't want them to be equal, make it obvious. If I had something where, instead of this example, maybe I'm skydiving, and there's a little bit of drag, but not a lot, and it's not gonna slow me down all that much, make it very obvious that they are different sizes. If I have something being pushed, keep in mind if I had a book being pushed across the table, gravity and normal are there because the table is pushing back up on the book as the book is pushing down on the table. I have an applied force because you're physically applying a force to it, or the book is having a force physically applied to it. If it's accelerating, then maybe this is okay. We notice we have no friction or drag or anything going the other way. So if we have an acceleration, this does not stand for acceleration, it stands for applied force. So, but you'll see unbalanced forces, I'll write this on the board, unbalanced forces yield an acceleration. So in this case, I have an acceleration. If I had a scenario where I was traveling at a constant velocity, and maybe friction was the reason for that, well, now my forces are balanced, and the opposite of this is that balanced forces yield no acceleration. And that could be a constant velocity, above zero, below zero, or it could just be zero. It may not be moving at all. The other part of force diagrams that you want to remember is that if something is on a hill, so if I have perhaps a box on a hill, and that box has gravity going straight down, gravity always moves straight down, the normal force is perpendicular to the surface that the box is sitting on, and then friction goes back up the hill. It's going to hold the box in place, or if the box is sliding down the hill, perhaps my friction in the line is a little bit shorter, and now the box slides down the hill and it accelerates down the hill because my forces are unbalanced. So they're going to look very much the same. The thing you want to be careful of is that there is not an applied force right here. That applied force would imply that something is pushing that down the hill, which isn't happening in our scenario. So force diagrams should be old hat at this point. Gravity, you may remember we did a lab on gravity earlier this year, where you stood here in the room, you held a ball out, we had a meter stick, and you had a timer. And when you dropped the ball, you hit the timer and started that. When the ball hit the ground, we stopped the timer, and we used an equation of 2d over t squared. We took the distance, which was 1 meter, and we doubled it, and we divided by our time squared. And we found the acceleration of gravity on Earth to be roughly 9.8 meters per second squared. So that's given the initial g. That's the variable that they've chosen for gravity of Earth, is a small lowercase g. 9.8 meters per second squared is in a vacuum. So if you were to do the test on Earth very accurately, and you did them not in a vacuum, you'd get slightly less than this. However, everything on Earth without air, or in the absence of air, will accelerate at 9.8 meters per second squared. So whether it is a piece of paper or a rock, if you drop them, that would be their acceleration in the absence of air. As we know, air affects things. It causes drag, just like water would cause drag for a swimmer. And so maybe it'll be less than that because there's a force pushing back up against gravity. But overall, if I were to find, or do a problem where I had to find the force of gravity, I would use the mass times the acceleration of gravity, and most of the time this will be on Earth. So if I'm looking for the force of gravity, perhaps I want to use my own, find my own weight in newtons. I know that I have a mass of roughly 100 kilograms, and I have an acceleration due to gravity of 9.8 meters per second squared. So I know that the force of gravity on me all the time would be 980 newtons. So I would be 980 newtons if I had a mass of 100 kilograms standing on Earth. Now if you went to a different planet, that could be different. Perhaps the moon is roughly 1.6 meters per second squared, so this person would only have 160 newtons of force on them if they were standing on the moon. If you went to somewhere like Jupiter, where the gravity is much larger, you would have a much larger force on you on the surface of Jupiter. So the important thing to remember is that this number, your mass, is constant everywhere. Whether you are on the Earth, on the Moon, on Jupiter, in the middle of outer space, it doesn't matter. 100 kilograms would be constant for me. This number is what changes. As this goes up and down, your weight changes. So if it's 9.8, I have a 980 Newton weight. If it's larger, that'll go up. If it's less, that'll go down. So the acceleration of gravity determines your weight. One of the other problems in a practice test was about an elevator. So an elevator was going up, going down, accelerating up and down. What's the deal with the elevator? Well, if an elevator, I'm standing in it, and I'm standing on a scale, and that elevator starts to accelerate downward. So I have a downward acceleration. The weight on that scale is going to appear to go down. Because remember, the weight is showing you what the normal force is pushing back with. If I have less normal force, that's what's causing me to accelerate downward. That means that it's not going to be pushing back as hard, and I will appear to weigh less. If we're accelerating upward, so accelerating downward, you appear to weigh less. And eventually, if you accelerate enough downward, you will be weightless because there will be no normal force at all. You'll be in free fall. If I'm accelerating upwards, I appear to weigh more because I have extra normal force pushing up in order to get me to accelerate. The third option would be that I'm traveling at a constant velocity. Constant velocity, whether up or down, means that I have a weight that is the same. So my weight will not change if I'm traveling at a constant velocity, or indeed if I'm just standing on the scale, because the force diagram would still be balanced with normal and gravity. The last thing we talked about in this unit was friction. And so that's the last force we're going to talk about here. The force of friction came with its own equation of mu, the coefficient, times the normal force. Now the normal force, in a lot of situations, and for us, has always been equal to gravity. And so in this case, we could say that the normal force is equal to whatever the mass is times g, which on Earth again is 9.8. Mu will always be between 0 and 1, coefficient of friction. As it gets closer to 1, it's a greater amount of friction. As it gets closer to 0, it's less friction. The force of friction, remember, if we have perhaps a force diagram, and I have the force of friction, maybe it's unbalanced. If it's unbalanced, then I can go ahead and solve for it. Perhaps I know the coefficient, or I know the mass. Hopefully both. I'm going to solve for the force of friction. You also may have a situation where it's balanced by an applied force. Maybe I'm pushing something, for instance, in a lab with mu of the shoe, or the static and kinetic friction lab. I knew this number. I knew the applied force. And the applied force, if you're traveling at a constant velocity, is equal to the force of friction. And then I can come up here and I can plug in what I know, and I can go ahead and solve for either mu or the normal force, or perhaps the mass, even if I took it a step further. So there's some stuff you can do with equations for the force of friction. There's also some vocabulary. If you remember, we had static friction, and we had kinetic friction. And if you break them right down, the easy way to remember them is moving and not moving. Static means you're not moving. So something sitting on the floor, me standing on the floor right now. Kinetic is moving. A car driving down the street, a block sliding down an incline, anything that's moving. static friction, or the coefficient of static friction, μs, is always greater than the kinetic friction if we're talking about the same two surfaces in contact with each other. It's harder to get something started moving than it is to keep it moving. In addition to these four topics, also want to be familiar with some different ways of force diagramming, and then just some of the other things that we've talked about as far as Newton's second law lab, and familiar with some of the data we collected and how that applies. For instance, if I graph the force of friction and the normal force, and I get a line that looks like this, keep in mind the slope is equal to the coefficient. We also had graphs in this time where we graphed force versus acceleration, and the slope was the mass. Now you could do that the other way as well and graph acceleration versus force, and the slope would be 1 over the mass. All of those things you should keep in mind for our quiz coming up and for our midterm coming next month. Thank you very much for watching. Best of luck.